coming out today. It's nice to see a room full of parents and family members who are here to support these scholars. This is the 11th set of presentations for the Scots Science Scholars Summer Experience. Really happy to have everybody here and to share with you a little bit about what has been going on these busy last 2 weeks. My name is Dr. Angela Gibson. I'm a professor of chemistry here at Maryville College. I've been honored the past couple of weeks to work with this incredible group of magnificent minds, such an inquisitive group of students that we've been able to work with this past 2 weeks. High energy, focused, really motivated. It's been a lot of fun. I work with my colleague, Dr. Maria Siopsis, who's professor of math and computer science here at Maryville College. We've been working together for about 13 years on this project. And so really great partnership, and I think that we've been able to have a privilege to work with a lot of brilliant people and build a program that I think is doing some good things, so I'm happy about that work. Also happy to work with Brett Longwith, who is our manager of STEM Success here at Maryville College. Just an incredible mentor and resource for our students. If you saw Brett in the last couple of weeks, some images of Brett might be on top of a trailer of kayaks, loading kayaks on, off in a corner talking to a student, listening intently to what they may need, maybe sending a text to Dr. Siopsis or to me saying, hey, we need to think about this as we revise this program next year, or we need to get this student in contact with this resource on the college campus so that they're well supported as they move into their freshman year. Those are just some glimpses of Brett. Also, I would say working feverishly yesterday, submitting an abstract for a presentation that we'll be doing in November at a scientific meeting. So those are just some images of Brett over the last couple of weeks. These guys are super lucky to be working with Brett and have him on their side advocating for them and watching out for them. We've also had a lot of support from our incredible team of peer mentors, and I'm going to read my list so I don't miss anyone. Ellie James. Ellie is an engineering major and environmental science minor. She's a sophomore and also a Scots Science Scholar alum. Camden Johnson. He's a biology major. Junior, also a Scots Science Scholar alum. We have Rory Walker, who's a biochemistry senior, a Scots Science Scholar alum. Izzy Wright, a biochemistry major, junior. And also Ben Wyrick, who's an environmental science major and also a junior. So really thanks to all of them. We also have several Scots Science Scholars alums who come out to listen today and who've been around this summer to help support the students, including Chance Loveday and Jorge Estrada Martinez, who are computer science and math majors, sophomores, who actually led our students in an activity this past couple of weeks, but also have just been around and really supportive throughout the program. So that's incredible. This program happens because of a lot of support from a lot of people outside this room on campus, and so we definitely have to mention that. And so happy. I mentioned Rory. I think, yeah, I mentioned Rory, but Rory also, okay. So Rory also led an activity with our students. So just a couple of notes about folks outside this room who or maybe inside the room, who are helping to support the program. First of all, the chairs of the Division of Natural Sciences and Math and Computer Science, Dr. Jennifer Brigatti for Natural Sciences and Dr. Jeff Bay for Math and Computer Science. They provide us a lot of support and advocacy, and we would not be doing this without their support, so we're very thankful for that. We had several faculty instructors this past couple weeks who led programs, Dr. Drew Crane in biology, Dr. Nathan Duncan in chemistry, and Dr. Ann Ray in biology, and you'll be hearing about the work that the students did on those programs. We also want to thank many of the offices and support programs across campus. So METS is our food service provider here at Maryville College, and it may seem strange to call them out, but let me just tell you, we have an incredible support team here on this campus. I cannot think of another college at which the folks in food services would send an email to a director of a small program on campus and say, This particular student was not on the list for this meal, and I just want to make sure that we've got our records straight. And so that's incredible that we had that level of support from them, and we're really happy about that. The business office, human resources, admissions, residence life, students affairs, all of those offices provide support for us. Of course, they're all under the directorship of our administration, and so our president, Dr. Brian Coker, our vice president and dean, academic dean, Dr. Dan Klingensmith, and our vice president and dean of students, Dr. Gianna Grant, also provide lots of support for our program and help make all of this happen. Finally, we have had just an incredible 2 weeks and have been able to do that in part because of partnerships outside of here at Maryville College, or inside outside. So Mountain Challenge is affiliated with Maryville College. They provide the team building for us. They will operate here on Maryville College campus, provide team building, and helped arrange for us to have an incredible opportunity that you're going to hear a lot about for us to paddle on kayaks through the Fort Loudon Lock. And that was supported, of course, by Tennessee Valley Authority, the Fort Loudon Lock operators, and the Army Corps of Engineers, so we're really grateful for that. Dr. Jay Clark here at Maryville College, who is our Director of Environmental and Sustainability Initiatives, arranged for us to be able to tour a company in Loudoun County, or in I can't remember which county, I'm sorry, Gianna is the name of the company, to tour a company that is using switchgrass and converting that switchgrass in a very environmentally sustainable way, converting that switchgrass and those products from the grass into paper plates and containers for keeping our food stored. And so our students were able to see that, the whole process, and tour that. You'll hear about it today. So we're grateful both to Dr. Clark and to Gianna for the opportunity to do that. We were in contact with Tennessee Aquatic Conservation Institute and Sanofi in Chattanooga, Tennessee, and they provided opportunities for us to tour their facilities and learn all about it. Of course, all of this happens because we had funding, and we have funding from the National Science Foundation. We have funding that comes through the Department of Education through a grant called a FIPSE grant that ultimately was sponsored by U.S. Representative Tim Burchett, and so we're grateful for the funding opportunities there. And of course, we've had support from donors and alumni here at Maryville College, and we want to give a shout out to Maryville College Alumni Association for inviting us to their event this past week, and we got to meet several alumni, and also I think the students got to have free ice cream. It was really good. So we're really grateful for all of that. So without further ado, I want to turn this over to the students, let them talk, and share with you all the incredible opportunities that they've had for this past 2 weeks. Thank you.
My name is Camron Easler, and my intended major is biopharmaceutical sciences.
My name is Patterson, and my major is biochemistry. During our summer SQ programming, we traveled to Chattanooga. On this visit, we visited Sanofi Aventis, which is a pharmaceutical manufacturing company. In our presentation, we're going to talk about the manufacturing and some instrumentation that both Sanofi and Maryville College use. But before we begin, we want to thank everyone who made this possible, which is Dr. Gibson, Mr. Delseld, Brett,
and the Department of Education and National Science Foundation for their grant in making these past 2 weeks possible for all of us and giving us the equipment and the funds to be able to do everything that we wanted to do. Now, for a brief history of Sanofi, Sanofi is one of the largest pharmaceutical companies in the entire world. They got this way by acquiring Chatham back in 2010 in a $1.9 billion deal. Doing this, they extended their history all the way back to the 19th century and the early 20th century, just starting out with your normal Band-Aids and cough syrup, your very, very basic fundamental stuff. But what is their focus today? Today they mainly focus on cancer research, clinical trials, and vaccines, your more heavy-hitting stuff. They cover major therapeutic areas as well, like your cardiovascular system, your central nervous system, your thrombosis, and again, vaccines. They're very, very big on those. And they're also very, very big on cleanliness, safety, and energy. They have the FDA standards, of course, but they think they're too low, so they shoot above and beyond They're really, really big on cleanliness and safety. They want to make sure everything is clean and safe. They always want more. Now, an overview of their over-the-counter medications. They make, I'm sure you recognize plenty of these medications. You've taken them before, or you may even use them on a daily basis, like Act Mouthwash, Allegra, Cortisone 10. Plenty of these I'm sure you recognize and see. Now, how you make those is where it gets really interesting. For solid manufacturing, this is your Allegra, your Rolaids, your Zantac 360. Now, step one is the feeders, which are used for their reliability and their performance. They're usually only used for 1 to maybe 2 drugs at a time. They're made to be as reliable as possible because they run continuously. You don't want to use them very much. They're all the time going. So you want them to stay as reliable as possible. Then you want to add in the non-active ingredients to get blended with the active pharmaceutical ingredients. Doing so is still your final dosage form. The non-active ingredients are your bases, and your active ingredients are what would be, for example, Allegra, which is what gives you, if you have runny eyes or a runny nose, which is to help stop that and calm that down. The step 3 is the milling, which is required to reduce the particle size in the drug powder. This is mainly used for tablets and capsules. For the capsules, this is to start compressing them a little so that they can fit inside the capsule, and the capsule can dissolve inside of you and can be dispersed into your bloodstream. And for the tablets, this is so it gets that nice chalky feel whenever you touch it, because it's just the powder compressed really, really tightly. It's just powder that's really heavily compressed. Now, the liquid manufacturing is quite different. That mainly consists of 3 tanks, and some of the medication they make from this is like mouthwash, icy hot, and Nasacort nasal spray. First tank tend to consist of sugar syrup preparation, and then the ingredient mixing and storage with product distribution piping. This consists of melting down the sugar, which consists of a base to help make everything go as good as possible. You want it to be a nice base that goes into all of these. And then you start mixing in your ingredients, like for your mouthwash, for example, to help freshen your breath, or if it is an alcohol-based mouthwash, that's where you would add that point in. And then then you go to the storage spot, which is your biggest tank. You add it into your storage. This is where you're adding everything in, and you're swirling and you're heating it, and just making sure it stays there until it's ready to go down the distribution pipeline, until you go down the conveyor belt and you start adding it into your mouthwash product cans or bottles. And cream manufacturing is also quite similar to liquid manufacturing. This is your cortisone 10s, your aspirin creams, and your gold bonds. The preparation of the oil phase is where they start adding the flakes and the water and gives it a nice base. And step 2 is the hydration of the aqueous phase ingredients. This is where they start adding in even more water, they start heating it up, they add in thickeners and emulsors to help start thickening up. This is where you start getting that cream feel that you know if you use like cortisone 10 or something. This is where you start seeing it and you start recognizing it more. Then the forming of the emulsion is when they start mixing it through in a very agitated process. They start heavily mixing it and they start heating it up even more and more because of how thick it's got at this point. Then the dispersion of the active ingredient. The active ingredient, for example, in cortisone 10, makes up a very small percentage. So you want to make sure that it's mixed very, very thoroughly, as if it's all at the beginning of the bottle, then once you get to the bottom of it, it's not going to be very good for you. What are you paying it for?
So one of the main methods of instrumentation used at Sanofi is chromatography. Chromatography is a separation technique where you take a substance and you separate it out into its individual components. For ion chromatography specifically, the components that are being broken down are cations and anions. Once you have broken down these substances, scientists can use these individual substances and can analyze a specific characteristic about them. For ion chromatography, the characteristic that we're looking for is their concentration. This is an instrument used for ion chromatography, and this is the output. Notice that all these individual peaks represent different cations. These are the different components that the ion chromatography instrument has detected. Now, why is this important for Sanofi? Sanofi Aventis uses ion chromatography to determine that the concentration of their ingredients are accurate and precise. This is how they make sure that all of their products that they make are the exact same. But how does it work? Ion chromatography works like this. You start off with a column in the stationary phase. The stationary phase is a sticky part right here. Now this sticky part is important because when you pour in your analyte is that substance that you're breaking down into different components. You put your analyte in the column and it adheres to that stationary phase. Moving on to the mobile phase. The mobile phase is where we're going to pour in a solvent. For ion chromatography, that's water. We pour in this solvent and what begins to happen is those different components are going to slowly move throughout that solvent. But because they're all different, they're going to move at a different speed because they're all stuck to that stationary phase differently. So for a component that had more stuck to the stationary phase, it's going to move less through that solvent versus a component that is less stuck. It's going to move further up. And so what you end up having is these different components, these different layers, and the ion chromatography instrument can detect that, and that's where you get those peaks. Now, after you get those peaks, it's time to find the concentration. And you do that by creating a calibration curve. A calibration curve has the concentration of the component on the x-axis and the area of the component's peak on the y-axis. And what we end up doing is creating a line of best fit. And this, we can use the slope formula. So we take the area of the component's peak on top of the concentration of the component, and we can find the concentration for our experiment. Now, one thing that's really cool with the grant that we got was we were able to use instrumentation that Sanofi Aventis uses. So real scientists used similar instrumentation that we got to use in our lab. So we did a lab with Dr. Duncan, where we got to use ion chromatography and we got to create our own calibration curves. So here, you can see this is one of our friends. This is Julia with her cute little glasses. And so we got to take local rainwater and we used a calibration curve and we were able to separate out using ion chromatography anions and cations in that rainwater, and it was really cool. Now, another instrumentation used at Sanofi is gas chromatography. Gas chromatography works the same way as ion chromatography, except for we're separating out gases this time. And just like how ion chromatography, right, we use ion chromatography to make a calibration curve to find the concentration of our components. Here, we're not finding concentration, we're finding molecular mass, molecular weight. And we're using that using a mass spectrometry. So instead of a calibration curve, we're using mass spectrometry. Here in this instrument, this part of the instrument uses gas chromatography, and this part uses mass spec. That concludes our presentation on Sanofi Aventis. We hope that y'all have learned a lot about the manufacturing and some instrumentation used both at Maryville College and at Sanofi. Thank you for your time.
So I'm Leilani Carden. I'm currently a finance major in environmental science.
I'm Aiden Stephenson, and I am looking to go into a business analytics major.
And we created a little presentation about population data and its importance to conservation. First, we want to say thank you to everybody who is here. Mr. Adam and Dr. Bernie were really helpful, and they gave us a complete program at Tenacity, which is what we're going to talk about today.
Dr. Siopsis for giving us some of the knowledge that for the math part that we use later on in the thing. Brett for helping counsel us.
And the peer mentors helped us a lot through this presentation itself and throughout the whole 2 weeks. And to the National Science Foundation and the Department of Education for funding this event. So the Tennessee Aquarium Conservation Institute is what Tenacity stands for. It's located in Chattanooga, Tennessee, and they promote conservation efforts of all of the southeast watersheds. So they actually protect 6 out of 8 of our bordering states, And they have some projects going on which benefit these species shown here, which are the brook trout, the crackling pearly mussel, and the Barron's top minnow. And these are currently being affected by overfishing, habitat loss, and then also water movement. So when dams or levees are put up, they affect fish's migration patterns for their So another fish that we learned about at Tanasi were lake sturgeons, and they're especially interesting because they are prehistoric. So since they were literally around when dinosaurs walking the earth, and they have not changed much, they can live to be 115 years old and about 10 feet long. Other types of sturgeon can grow even longer, to like 20 feet. And they were almost pushed to the brink of extinction in Tennessee because of overfishing for their caviar. So they are trying to bring them back at Tennessee. And one special challenge about them is that they have to grow to be 11 years old until they start actually reproducing. So we have to make sure that they are being sustained, not just being raised, but also all the way to them, so they can reproduce. So their specific project is, it's like a multi-step process. So first they go to the actual place where they're trying to reintroduce sturgeon, and they will get in the water with waders on and count how many sturgeon they find, and then also their ages. So then they go out of state to a sturgeon hatchery, and they collect the male and female parts for them, and then they're like mixed up in this little bowl, and they're brought back to Tennessee in these special aerated tubes so that it replicates their natural environments. And when they're big enough, and so you can see them. Oh, okay. So you can see them right here. This is where they're raised, and they're really little. And these are all the 3 same technicians that went to school. And then here they are, and this is the stage called fingerlings, so they're about the length of like a pointer finger. And then here they are actually releasing them. So these are managed really carefully while they're being raised by water filtration and then also daily water tests.
Even
at Tanasi, one of their tenets is public outreach, and so they actually do public sturgeon releases at our local lakes in Tennessee, and they've released over 330,000 baby sturgeon in the last 22 years. So that's a great way to get involved if you're interested in this.
This is Edes, and they are unique to Tennessee, and they have become endangered due to the droughts and habitat management. The data that's been collected on them has been able to be used to create predictions through equations on the yearly progression of the population through the life cycle. And as you can see, they all begin here at larval and juvenile, where only 1.2% of them make it into their first year of life. And the first year of life, the females kick back 135.5 on average per female. Then next year you have a pretty good step up to 15.3% survival. And as they mature, they produce more eggs, this time having 200.5 eggs per female. Then year 3, they don't survive quite as well, say 5% survival rate, and they kick back at 284 eggs. With this information, we can use Leslie models, with both of these being examples. The bottom one being the model Dr. Siopsis taught us with, and this one being our example application showing butterfly stages, because they have butterfly gardens over at the Tenacity facilities. And with the Leslie model, you start off with your initial population and then you put in equations. With each equation, it takes a percentage you multiply by. So for example, with the days, year 2, after having 100 released into the natural population, you have 240 eggs, 28,400 eggs. Then only in year 3, you only have about 1.5% of that still remaining. And you keep going, and eventually you end up with 90% of your population in the egg/larval phase. Although Leslie models are good for a rough estimate, Tenacity prefers to go in and get their hands dirty or wet in a way of speaking, and they like to go manually count the fish. And whenever they go out there, they can account for new data that they didn't see, like an illness happening or a destruction of habitat, and they can use that to update their data.
Yeah, so that's just.
They face similar issues. At least while we were doing Dr. Siopsis' lab, we found a lot of trouble finding population data. So it's really important that that's being updated constantly. And we also learned at Tenacity that even though we're in the most biodiverse area for aquatic life, there is a huge difference in funding from here compared to like out west. So really hoping that we can support and change that moving forward. Thank you so much. Does anyone have any questions? Sorry. Okay, cool, thanks.
Now I know that's hard for them to survive. That's why they don't multiply. That's not all right. That's not the structure. They have armor. They're also. I've seen floats in high school. But usually they're down. They're like that. They're like to be on the bottom. Yes, they're down. And they're usually down in the diamonds too, because that's where the deals are.
Oh, it goes on the
No.
Yeah.
Here's our minute for the ad break. This is not the update.
My name is Gianna Mantegna, and my major is going to be environmental science.
My name is Obasola Immanuel, and I'm going to be doing computer science. And this is our project, Javascript coding and Microbits.
So over the past few weeks, we've been doing a ton of labs, and one of those labs was Microbit Lab, which was led by Chance and Jorge, two of the students here. And we had, honestly, so much fun with it. What they did was they used a website called Microbits, which is part of like this whole program. And I have no idea what that is. That's never popped up before. Oh, it's the mouse. I'm so sorry. And through this website, it shows you how to do block coding, but it also has an option for JavaScript coding. So we're going to show you guys the basic building blocks of code that we were showed in the lab, and then also how we used, going from those blocks to JavaScript coding to create our own program.
Yeah, so we use the microbits. So briefly show the microbits. So in 2012, BBC UK announced the Make It Digital campaign, which was made to encourage digital literacy and programming for 12 girls and 11-year-olds, which are the 7th graders there. The project was aimed at distributing microbits to students in the UK, which would foster interest in coding and digital creativity, basically. In 2016, it was launched, so 1 million microbits were given to schools in the UK, and this was done basically to encourage digital literacy and interest in technology and coding. And then after a while, after the initial rollout, schools gained popularity, and then schools started to get interested in it, and then they started to get more microbits across the globe, and then they created a Microbit Foundation, which would support teachers and help them teach students and coach teachers and how to teach students about coding and basically basics of coding. And then in educational impact, it teaches coding, teaches programming, and it helps problem solving skills basically. So how do microbits work? We have two, as you can see on the microbits, this is what it looks like on the front and at the back. So in the front we have two programmable buttons, A and B. And this is basically your input functions, and then we have 25 LED lights, which are for simple animations and help you to see what you're programming. And then we have the USB connector and the battery socket, which are the two main power points. So if you don't have a USB connector to your laptop, you just carry a battery socket, which allows it to be portable and more useful, and you can carry it around. And then we have multiple pins for sensors, because it only comes with a compass and an accelerometer. So the multiple pins allow you to do more projects with it and allows you to do basically more stuff. And the reset button for your codes.
All right, so we wanted to show you the game that we were taught how to make in the lab. So I'm going to go ahead and pull that up now. So, do you want to put this on the camera?
Okay, so Simon says, so basically it's gonna, when you play it, it's gonna show multiple signs, and then you have to pick the right one basically. So
this is like a simulation of what you can do with the actual microbit that I handed you around here. So over on the left side is the digital display. So if I hit A, the game will start, and it'll show me a symbol, and then I just have to replicate the symbol, hopefully correctly, otherwise I get a game over. Sorry, we'll try that one more time. So start the game again, and then as soon as I do it correctly, it'll give me a little beep telling me that I've done it correct, and then I'll purposely fail this. Oh well. And then, yeah, there's the game over for it. So there's essentially 4 main functions that you would use for this. So here's the block coding, and this is what Chance and Jorge showed us how we make it. And then this right here is the actual JavaScript version of it. So functions are super important for creating code, because it's a really simple way to break up the code and have like different sections for what you want things to do. So this is the section that shows us the sequence that you saw, those 3 triangles that appeared on the screen. So we also have the for function here as well. So if you've ever in math done the sigma, the big E that's got numbers on top, numbers on bottom, that's essentially what the for function is, just in code. So it's got a function that will repeat a certain number of tiles a certain number of times based off of the inputs that the computer is receiving from you. And then we also have the check sequence function. So this is an example of an if function. So if something is true, then we'll execute this code. So if you don't have the correct sequence, it's game over. But if you do have the correct sequence, then it will show that little tone and the little check mark that you guys saw.
Okay, so the next sequence is the iTile function, and basically it's a randomizer for the items or things that were shown at the game. So basically, we have three functions, and then in arrays, it goes from, the index starts from 0 instead of 1, so that's why it's 0 to 2 instead of 1 to 3. And the game over is basically the same thing, it's simple. So once whatever you play is false, then the game stops, and then you start again, you have another chance to start again.
Yeah, so this is the game that we created using the same concepts in the Simon Says, that for function, the if function, a number randomizer, all of the functions. That's what we did to create this higher or lower game. I don't know if you guys have ever played it, but you'll get to now. So here it is, and this is the code is on the side, and I'll show you guys snapshots of it later, so you don't have to worry too much about reading it. But if you look in the green right at the top here, this is what we call pseudocode. It's not really going to run the function, but it's a really good way of explaining what I want the function to do. So essentially, all this function is going to do is it's going to create an array for 52 cards, because it is kind of a pain to type out all of the 52 cards that you want in that deck. Then it's going to select a card and display the selected card for you. It'll remove that card from the deck because you don't want to draw it again. And then it will ask you for input. So, you get a card, it asks you higher or lower, and then it will after you tell it something, it will randomly select another card, judge if you've won or lost, and if you've lost, you lose, or you'll continue until you eventually lose, But let's play. So this is a 5 of spades. So you guys, do you think the next card will be higher or lower than a 5 of spades?
Higher.
Awesome. You were correct. All right, this is the Jack of Hearts.
Lower.
You guys are good at this. All right, 10 of Diamonds.
Lower.
4 of Hearts.
Higher.
Oh my goodness. Jack of Clubs.
Lower.
Okay, we're gonna have to fail some next. All right, 6 of Clubs. Well, I heard a little bit of dissent there. We'll go with higher. Wow. Okay. I'm gonna start picking stuff. Okay, I said lower. It was King of Diamonds. I was wrong. Game over. You guys are very good at this. All right, so let's look at what's actually going on behind the scenes here.
Okay, so the first function is a start function to create the deck. So basically, you have 52 cards in the deck, and then this is what it does. So when you say function start create deck, and card select, so it basically picks out a card for us to play, and that's the first card we see, and then it continues to bring out more cards. And then the next function, so there's basically 4. This is create diamonds, but then there was 4. There's create spades, create clubs, and create hearts. I just showed one here. So this is the 4 function again. So it basically loops and continues to bring out more cards. Basically brings out more diamond cards. So the ace of diamonds, king of diamonds, queen of diamonds, jack of diamonds. These are the special ones because there's numbers. So it starts at 2, and then it goes to 9. Right, but then, so it just loops through, and then it goes from 2 to 9, and the I++ means it keeps adding more numbers, so it goes from 2 to 3 to 4, and then to 9, but then, since the ace, king, and queens are different ones, so then we put them here. The randomizer, so this is another function for allowing the cards not to come on the right, so basically if you have like a hearts, ace of hearts, then they probably will bring out like a 9 of diamonds or something. And then the 0 to deck of length of -1. So this is basically bringing out from 0 to 51 because there's 52 cards, and like I said, in arrays it goes from 0 to the next number. So instead of 51 to 52, it goes from 0 to 51. And then as we keep going through, it keeps removing cards and keeps storing them in a different place so we don't bring up the same card next time.
All right, so here's our if-else statements. This was a little bit of a big one, but this is our check function. So very similar to the check sequence function that you saw earlier. So this is, so it's saying that if you made the correct option and it actually matches, like, if you pick higher and the next card was actually higher, then you win, the game will continue, and it'll pick another card. If it's a tie, which we didn't get, it'll say it's a tie, and then you will continue the game, or it will end the game, and then the game will be over. Okay, so this was a really fun project, but I must admit that coding all of this in 2 days definitely had its struggles. I think the most important thing that we learned from this is checking the definition of variables, because there's a lot of moving parts in this thing, so making sure that you're calling the right thing and making sure that it means what you want it to mean is super important. You've got to retest and retest the code. I can't believe how many times I hit go and then it broke again in a different place and I didn't even touch it. So definitely a ton of problem solving. And then this is my duck. I have a picture of her here. I like to talk to her because she's real brains behind this operation, because it can be super useful when you're coding and you don't know what's happening to explain what you want it to do, and then be like, oh, maybe I didn't add this, or maybe I didn't change this, and it's just honestly super useful to talk to something when you're not entirely sure what's going on. So this is my duck. Her name is Pinky. I can show you guys her later. She's awesome.
Okay, so JavaScript is one of many programming languages, and then there's more stuff we can do with programming languages, like create websites with Java, HTML, CSS, and React, mobile applications with JavaScript and Carden, and data analysis with R and Python, and games with C++ and Python. And then
Yeah, so piggybacking off of that, you can use coding for anything. So here's just a few of the labs that we did. So this is actually an example of our coding that we did with Dr. Bay in his statistics lab. I did modify the code a little bit just to, I don't know, I thought it looked, to make it more visually easier, because these ones go in quite a bit into the middle of the circle here. But if you were to, you can use coding for anything. So with the Dr. Crane in the orchard lab, you'll hear about that later. We were counting apples and we were measuring tree diameters. There's really, if you created code for it to just plug in all of those things to get back a result that you want, that would be super easy. Or with Dr. Siopsis and the fisheries lab, if you would like to plug in some numbers and get, you wanted to ask after how many generations, how much fish will there be in year 2? That could be something that you could code using code. All right.
So thank you to George, Dr. Martinez, and Chancellor Day for teaching us. Ellie for helping us with our work and making sure that Chance could help us. And Izzy
For the pictures.
for the pictures. And then the National Science Foundation for funding and the Department of Education.
And then our references.
But yeah, our references, we use these guys.
I'm sorry, I can't see my
Hello, my name is Angelia. I am a food major.
I'm Jared Law. I am a mechanical engineering major.
And we're doing Orchards of Maryville College. We are the Scots Science Scholars of 2023. A couple of days ago, we got to go with Dr. Crane, and we have two orchards here at Maryville College. We grow pears and apples and I believe peaches or nectarines. I'm not sure which, but we had the chance to go and measure tree diameter and count how many apples there are on the trees. Okay, the first of which was the mill orchard. The hypothesis was that the mill orchard would have more fruit and fuller trees because it has a higher phosphorus content. A higher potassium content and a lower phosphorus content. You want more potassium in the soil of the orchard, because the potassium helps the trees take root better. As compared to the Browns Creek orchard, which has a higher phosphorus content and a higher potassium content, there's us with Dr. Crane. And here's the data we collected. As you can see from the graph, the tree diameter, okay, so trees 1, 2, 3, 4, and 5 were in the Browns Creek Orchard, and trees 7, 8, 9, and 10 were in the Knowles Creek Orchard. As I said, the hypothesis was that the trees in Knowles Creek Orchard would grow better because of the difference in the soil content. The diameter, as you can see, is higher in those trees. There's a caliper, that's how we measure the diameter. And here's the apple count. The apple count was not necessarily better, more accurate as far as measuring how well the trees grew, because there were a lot of variables with apples. The fruit could have fallen, could have been eaten by wildlife. We have a lot of bats. We have bat boxes actually over in the orchards. You'll see a picture of that in a second. There's fire blight, which is a bacterial, it's a bacterial disease. It makes the trees look burned. And the incident. A couple of years ago, 2 years ago, there was a student who accidentally cut off a very important part of the tree, which was the central leader, which is where all the other branches sprout from. They cut that off by mistake, but only on the trees in the Knowles orchard. So that was a big reason the apples in the Knowles orchard weren't as plentiful as in the Browns Creek orchard. Now, our orchards take a lot of pride in the fact that we don't use any pesticides or herbicides. Pesticides and herbicides, the reason we don't want to use those is because they can actually be really detrimental to the environment if used improperly. Pesticides, if used incorrectly, they can seep into the soil and then be taken up by the roots of other plants. And when bees and bats and other wildlife eat or use those plants, they can actually be harmed by the pesticides and herbicides that were not intended for that. And further than that, if it rains really hard, sometimes the pesticides and herbicides can be washed off the plants, soak into the soil, and in the stream runoff go into the stream, where it can be detrimental to the plant life and the animal life in the rivers. And there's over-fertilization, leading to excess of nitrogen and eutrophication. I'm sure you've seen pictures of those beautiful, clear, crystal clean lakes on the internet. That's actually really unhealthy lake, because what happens is the fertilizer goes into the river and streams, and the algae soaks it up and grows tenfold. There's so much algae in the rivers and streams, in fact, that the fish could quite literally suffocate it, because all the algae soaks up all the dissolved oxygen in the water. And as the fish are suffocated, there's no fish to eat the algae, and it becomes a cycle until all the fish are gone, and then all the algae, literally, there's no more nutrients or available resources in the water for the algae to grow. And when the algae dies off, the crystal clean lakes like that. Now, part of what's helping keep our rivers and streams clean, and to help take care of our orchards too, is TNASI, the Tennessee Aquarium Conservation Institute. The trees near river streams play a very important role in keeping the rivers together, because the trees on the riverbanks help keep the riverbanks actually intact. They prevent erosion, the roots do, and they provide shade for the fish. They provide homes for the animals that maybe are use the fish and the wildlife in the river to live off of. There's a brook trout, a river trout, and a tangerine darter. We all saw those at TNASI.
So an important thing to remember about taking care of your orchard is there are three main things. Typically, certain animals such as the invasive Japanese wood beetle can harm trees. In Japan, these creatures are naturally regulated in the life cycle, but here in America, they are a threat to more than 300 different types of plants, and they typically eat between the veins of leaves in our trees. And another two sources of concern are both fire blight and improper pruning, such as when the central leader is removed. This is the main tree that sprouts up from the very center of the tree, and it's where all other branches sprout out from the tree. So once it's gone, there can be innumerable branches from the tree that grow straight up. And fire blight is a bacterial disease that can spread to other parts of the tree. It causes blackening of the wood and wilting of all the leaves. So it's important to remove those. So important factors of orchards, they're also good sources of food for both wildlife, of course, and people, of course. They're sold locally at farmers markets and local stores. They're useful teaching tools for pruning and grafting, and they can provide shelters for animals such as the bat boxes that are kept in orchards as well. One tree can produce 260 pounds of oxygen per year, just one. So an entire orchard, you can only imagine how much oxygen that can provide. Along with about 20 tons of carbon dioxide it can absorb. And obviously the food for wildlife, again, the bat boxes here, and the bees, and small mammals. The bees and bats, those are important as well because they're just major pollinators for the areas, especially. So the typically fruits, figs, they're grown in these orchards. The best times to plant for these orchards is early spring or late fall. It's unlikely that during these times there will be a sharp drop in temperature, so it's important for those times. And when digging holes for these plants, it's important to keep them in a square shape so that the roots have a better way of rooting themselves into the ground, making sure that they're stable. And now we're on to the actual parts of taking care of the orchard, such as pruning, grafting, and the fertilization process. Now, pruning and grafting, they're similar but different. Pruning is a process of removing undesirable branches from trees. It's typically for things such as fire blight or trees that have been too successful and have begun to collapse under their own weight, which can risk smothering other plants, preventing them from receiving sunlight and oxygen. So it's important to remove those parts of plants. And grafting, which is the process of taking broken branches, an upper half, which you plan to attach to the tree to control the growth of it. That would be known as the scion, and the rootstock, which is still attached to the tree. These are the two parts that you would connect. And for the fertilization process, it is usually required that 2 to 4 pounds of fertilizer per the diameter of the tree is used per tree.
And we'd like to thank the following for making this presentation possible. The amazing Dr. Drew Crane for taking us into the orchard, the people of Tenasseee, the awesome animals in Chattanooga, and the Department of Education.
So my name is Braxton Whitehead. I'm a computer science major.
I'm Tucker Smith, and I'm an engineering major.
I'm Braeden Barrett, and I'm a biology pre-med major.
And this is Locks from Debs. First, we just want to say thank you to all of the companies that made this possible. We had a lot of fun in these 2 weeks and learned an awful lot about any part of the STEM field that you could imagine. Gianna, thank you, and Sanofi, thank you for letting us tour your facilities. That was really cool. And we'd like to give a special thanks to the Navy Corps of Engineers for letting us kayak through your lock. That's what we're going to be talking about, and really what piqued our interest in this whole thing. So why locks? Like I said, we were able to kayak through the Fort Loudon Dam through their lock, which was really cool, and we found it to be really interesting, and they made it really clear how important locks are to the lakes and just the natural wildlife and movement of products through the river systems.
So I'm going to talk about the history and adaptations of locks when they were first created, how many different types of locks there are, and how and why the Fort Loudon Dam and locks was created. So first we have the lock history and progression. The first lock ever seen was in 3rd century BC in ancient Greece. It was said to be a simple yet very efficient lock that allowed through many boats to go through to connect to different smaller cities or even bigger ones. And then as time progressed on, the first canal lock was created by Chai Wei Kyo, Asian engineer, in 983 AD. And his version was a little bit more, not a little bit more, a lot more efficient because it allowed for not only boats to go down, but also go back up and against the stream. And here we have Leonardo da Vinci's drawing of his own lock, and he created a bunch of different types. But as we talk later on in the presentation, you can see how today we have adapted to using these very old drawings that 45-degree angles on the doors. So there are multiple types of locks, and they have all different types of uses. So there's a single lock, a broad lock, and a double lock. There's also stop, guillotine, and staircase. The stop, guillotine, and staircase locks aren't really used anymore. They're more during ancient times. You can still find some, but not a lot anymore. But what is mainly used is a single lock, and you can find that at the Fort Loudon Dam, but each type of lock depends on the area you're in. So like, obviously for the Fort Loudon Dam, you have a bigger area, so you're gonna have a bigger lock, so you can allow for more things to go through. But for their smaller areas like Amsterdam, you need to use things like broad locks, which allow for a couple of boats to go through, because you still need for more boats to go through, but there's not as much travel, so it doesn't matter as much how fast you get boats through. But then there's also other places in Amsterdam where you have higher traffic areas, so you need to use a double lock that allows for boats to be risen up and taken down simultaneously. So as I said before, each have their own specific and unique uses. And for the history of the Fort Loudon Dam, construction began July 8th, 1940, and there were 3 phases to the making of the dam. First phase was the lock. This is where we were able to go down, and here it is. We were able to go down and kind of watch slowly. It kind of took a little while, but slowly we went down. You could see just how high up it really was. And then phase 2 was the spillway. The spillway is where if there's an excess of water at the top, they would have to open the gates so that they could lower the water level at the top, or vice versa. If there's not as much water at the bottom, they need to be able to raise the water level again to make sure like everything's even. And then finally, the third phase was the powerhouse. This is where all the energy is created in a hydroelectric thing, which you'll learn later they used as a part of the energy for the opening of the lock system. Oh, and then the construction ended in June 1944. And they said for the main reason why they created this was to help the Tennessee Valley River become better and more efficient, which is why they created the hydroelectric dam to get energy throughout the east.
So how a lock works. The first part that's really important is the first door. So where a lot of ships and us as kayakers entered from. These 2 doors are actually at a 45-degree angle in order to make it easier to just open them and just keep them shut, because instead of pushing the water on 2 horizontal doors that keeps it open, it actually pushes the water and keeps them closed. So this allows them to use less energy when they're actually opening the doors and doing anything with them pretty much. They only have to use a 10 horsepower motor to actually open the 2 doors, and that's the only energy that they use. So how the lock fills up when the doors open. So there's a well right here, right before the doors actually start. And once they fill up that entire area, it starts to come up through these 2 little, or it can be 2, it can be multiple holes in the bottom of it, and it will start to slowly fill up. The one we actually went through filled up 12 million gallons of water, and that's about average, I'd say. Once it fills up, they will completely open the doors and let barges, ships, whatever they're locking through into the actual area. So the time it takes to lock. They're very efficient because it only takes about 45 minutes to an hour to complete a complete cycle. So bigger locks can fit 3 or 4 barges inside of them, and it only takes 45 minutes to an hour to complete a full cycle, which sounds slow, but it's actually quite fast when you think about how big a barge is. Each one can fit about 60 semi-trucks worth of product on them, and so if you're fitting 3 or 4, that can be upwards of 240 semi-trucks worth of volume that went through in 45 minutes to an hour. And here's a short video of what it looks like.
Well, maybe no video today. So the locks and dams affect surrounding areas, such as the fish population, tenacity conservation, the soil pH level, switchgrass, and a company called Gianna affects their production as well. So for the fish population, the locks could create barriers for migration, so the fish can't always get through the lock because they'll close it and they can't get over to the other side, so they're restricted to one side of just one area where they have to stay. They can't always get through and get to the new feeding and spawning grounds to where they can't reproduce on the other side, where they can't spread. They're only restricted to that one area, where that can sometimes kill off some species and some populations of fish. So the Tenacity, which is the Tennessee Aquarium Conservation Institute, I think another group before us had told us a lot about it. We took a tour of it and they showed us all their facilities and showed us what they do. So these locks can obviously affect the fish population, which makes it harder for the Tenacity to count all the fish and to take all the populations of that. And then so the migration patterns change, so they don't always know where to look for certain fish that they're trying to find a population for. And so their biggest thing is keeping the species diverse and trying to keep a lot of different fish population species, and the locks make that more difficult. So for the soil quality and pH level, so the water downstream could always affect the soil and erode it sometimes, and water tends to be more basic, so for the pH level for the soil, it gets into the soil and makes the pH level higher, which is more basic, and it makes it makes it better for crops and plants, and makes it grow better. Then switchgrass and Gianna actually is a company that we toured, so I think Dr. Gibson talked about it, but they make these takeout containers out of switchgrass, and it's biodegradable, and it's much more it's a lot better for the environment. And so how the locks could affect switchgrass growth, it could like when it helps the soil out, switchgrass actually the roots of switchgrass are a lot deeper. They go a lot further down to the ground than other crops, so it'll hold the soil there better, so like the water won't wash it all away. So then either switchgrass you can plant more or plant a different crop, and the soil is going to be better for a longer time. And then that helps Gianna because they make their stuff out of switchgrass, and they're going to have more switchgrass and more healthy plants to use for their products.
In conclusion, the main points we wanted you to take away from this is that we were able to have a great time going through the locks. We learned a lot of things about it. We were able to learn how it can not only help, but kind of make our environment better. But at the same time, there's also downtakes, like the way it kind of takes away from the fish population, and also how locks up in here for a long, long time.
Hello, everyone. One more. I'm Aiden.
I'm Miles.
And I'm Julia. And we are presenting on the BioBits and Polymerase Chain Reaction Lab.
So the first thing that we want to talk about before we talk about the labs is the central dogma,
And that's basically a statement that says genetic information travels in one direction. So if you look on the next slide, our main focus is DNA through both of these labs and the different processes that they undergo. But first we want to talk about transcription and translation. Our first lab, we are going to focus on those two processes. Transcription is when DNA separates and then one strand of it is coded to create messenger RNA. And basically the messenger RNA will then go through translation to make protein. And there are different molecules called tRNAs as well as ribosomes that will help that process go through. So the first lab that we're going to talk about is the BioBits lab. And basically a BioBit is a small pellet that has those tRNAs, those ribosomes, as well as the ATP, which is energy, that is used for both transcription and translation. So we're taking those BioBits and we're putting them in these little tubes and we're adding DNA to them. And we're also adding fluorescent molecules that will let us know that the transcription and translation processes have occurred. The mRNA will be a fluorescent green color and protein will be a red color. And we built these little boxes that have an LED light in them that we can pass around. And you can see those tubes inside with the fluorescent green and red colors. So the materials for this lab, so we have these 4 tubes. Tube 1 was used as a control. So we added no DNA to it and we just added our reagent, which was water. Tubes 2 and 4, we used the same amount of DNA and reagents. However, we did use 2 different types of DNA that can be used for variation to see if they would react differently. And then tube number 3, we added the same amount of DNA, but we added an antibiotic called kanamycin, and we wanted to see what effect that had on the processes. So the procedure of this lab, we used micropipettes and we did a lot of practice with them, and it's very important to use precision when using micropipettes. We want to make sure that they're calibrated properly to the right amount of microliters, and then we also don't want to cross-contaminate. So after mixing the DNA and the reagents, we switch out the tips so that we don't cross-contaminate. After we mix all the reagents and DNA in the tubes, we put them in that box and we record our observations at 0 minutes, 15 minutes, and 24 hours. So after 24 hours, this is what it should look like. Tube number 1, we added no DNA to it, so it was unable to go through transcription or translation, so it just remained a dark yellow color. Tube number 2 is the one that we got the most results from. It turned red, meaning it went through both transcription and translation, and the red should be protein that we made. Tube number 3 only went through transcription because we only saw fluorescent green color, and that also is the one that had the kanamycin in it, so that shows us that it stopped the translation process from happening. And then tube number 4 was the other DNA that we used, and that also did not go through translation, just transcription. I was going to talk about this one.
Okay, so the next lab we did was PCR and gel electrophoresis. PCR stands for polymerase chain reaction and was used to amplify specific proportions of DNA. And then the primers and DNA polymerase enzyme were used for this whole process that I'm about to go through. The procedure we did, we micropipetted PDR12, PDR1884, a bacteria sample, primers, master mix, and water into these like PCR tubes. And then the thermocycler, which is like, it's like a clear box that we ended up connecting to like a computer, and it like heated up, and we left it in there we put the tubes in there and we left it in there for 2.5 hours. And after those few hours, we found over 33 billion strands of DNA. And then after that process, we put it in the electrophoresis instrument. And the way this instrument is set up, it's like there's a starting position, which is where the wells would be, which is at the top. And all of our DNA molecules would start up here because they're negatively charged. and the top is negatively charged and the bottom is positively charged. And the longer DNA strands move slower because they're larger, and the smaller ones move faster because they're smaller. But yeah, over time we just saw like the movement of the DNA molecules. And then this is the process of like how it all works. Denaturation is the splitting of a DNA molecule into two separate, like the long ones that you see right here. The annealing process is what's circled right here, is where the primers are introduced, which are, again, the smaller pieces that you see at either end, and in that process they connect to the longer pieces. And then the extension process period, the DNA polymerase is introduced, and it basically finishes the rest of the strand with its equal base pair.
And so this is our results. As you can see, we calculated them mathematically. This is the gel which went through the machine that Niles was talking about, or the instrument, excuse me. And you can see this is our ladder, this is our control. These are known measurements. It's found by the molecular weight. Up here, this is graphed. You see on the y-axis, we have the log of the molecular weight, which tells us just how big the piece of DNA is, and then the relative mobility, so how far it moves. So you can see the line that says if it's bigger, it's not going to move as far down, based on the charge. It's just like magnets, kind of. And so this is our equation, and we found these small ones that were down here were the samples that actually moved. Our other ones didn't react because sometimes the primers don't actually match the DNA that we were given, so they didn't actually have anything that would move. So the PDR12 was the one that we found that was able to be seen, and it had a molecular weight of this with that many base pairs, and I just think that's kind of cool that you can do that with math. So we can connect both of these labs, both with the BioBits and the gel electrophoresis. DNA went through a polymerase chain reaction, but two different ways. So in the BioBits, it went from DNA to mRNA to protein, and then we were able to see that visually through our P51 box. And then in the gel electrophoresis, we were able to see all of that DNA being replicated in the wells, in the gel.
Thank you.
These are also our citations. And we'd also like to give a great big thank you to all the people who made this possible. We would like to thank the Department of Education and the Fund for the Improvement of Post-Secondary Education, the grant, and the Office of Tim Burchett for making this possible, giving us the money to be able to do this, as well as the National Science Foundation, Dr. Stephenson, Dr. Gibson, thank you so much, Brett, peer mentors, everybody who was part of this that made this such a wonderful experience. Everybody listed here as well. And I think we'd like to thank each other for making this such a really fun experience, and just teaching each other things that we didn't know about and learning about ourselves more. Let's give everybody on this slide a big round of applause again.
This might always be my favorite day of the program. We do a lot of fun stuff, and I get to spend a lot of time just being with the students, which is my favorite part of the job. But today, I get to see these students come speak about technical, difficult things and do it really well. And to see that growth, and to see them grow in confidence, knowledge, skill, and begin those first steps of their journeys to becoming scientists, mathematicians, computer scientists. That is amazing for me. So I would like to give all these students yet another round of applause, because I'm really proud of you guys. So yay. I'm going to say a few things. Hopefully in this 2 weeks, you all have I've seen you do a lot of learning. You've learned a lot of skills, that was obvious. right, from your presentations, and a variety of skills. And some of you are, like you said, I'm a biochemistry major, and we suddenly made you do coding or statistics of sports, or vice versa. You're a math person, and we threw you into a wet lab, right? Which I mean, I don't know how to do those things. So you've really, and this group has really jumped in both feet. We talk a lot about identity and culture, and each group of the 11 always has a different identity and culture. And I was thinking about, what is this group's identity and culture? And a lot of this group's identity and culture is the hard-working, task-oriented, on it folks. So, wow, you're already at the, you haven't even started college, and you already have those focused, that ability to focus and put it down and work. And oh my gosh, you guys don't ask for breaks, right? I remember doing my lab, and usually like you can see the sort of like, oh, like they need a minute, and we're just going. It's like the Energizer Bunny's here. Wow. So really, what I want to tell you is that I want you to carry that identity, carry the learning, carry the growth, the curiosity. That was the other thing I meant to talk about. The other thing this group has is a real curiosity, and I mean, we have never had to say to a group, look, you've got to stop asking questions so we can go on to the next thing. I mean, we were touring facilities, and this group is asking all kinds of great questions, impressing our guests. Definitely our guests were like, hey, if anyone wants an internship, like, so wow. So you have this foundation now, right? And on top of the foundation of skills and learning and attitudes, you have built a team of folks that are your people, right? So you guys are, next week, like literally at this time next week, most of you will be sitting in a class, right? In a week from now. And in those classrooms, you will see some of these faces. And during the semester, there will be moments. There will be moments of, yes, I got that. I'm doing really well. And there will be moments of, oh, this is so hard. And in those moments, let's look around for the people in this room. Look around for your peer mentors. Look around for Brett. Look around for us and each other, and share that. Share the happy. Share the tough. Share all that. That's what we're here for. Mm-hmm. So what I want you to take is this foundation that you have built here, and I can't wait to see what gets built on top of that foundation for each of you. There's already people talking about, oh, I'm not sure if I want to do that major or that major, all these good things. So take that with you forward. I am so proud of you, and I am so optimistic about the things this group is going to do. Congratulations. You're done. Yay.